Welcome to Nexted, a tech education initiative by Nexaspaces. Today's topic is a foundational one for every embedded system enthusiast. Interrupts, timers, and delays. These aren't just terms, they are powerful tools that control how your microcontroller thinks, waits, and reacts. From blinking an LED to building real-time IoT solutions, these mechanisms decide how efficient and responsive your program is. So whether you're just starting with Arduino or diving deep into ARM programming, this session is going to sharpen your skills. Let's get started. Let's begin with delays. A delay is the simplest way to pause the execution of a program for a fixed amount of time. Think of it as telling your microcontroller to do nothing for a moment. For instance, if you want to blink an LED on for 1 second and OFF for another, you use the delay function. Here's how it looks in Arduino. Turn LED on. Wait. Turn LED OFF. Wait. Repeat. Under the hood, what's really happening is that the processor is idle, it does nothing else until that time expires. Now, that's fine for small, simple tasks, but here's the problem. Delays block the CPU. You can't check a button input, you can't read a sensor, nothing else runs. It wastes precious clock cycles. In embedded systems, this is dangerous if your system needs to respond to real-time events. So while delays are easy to use, they limit what your microcontroller can do at once. To overcome the limitations of delays, embedded systems use a more powerful feature, timers. A timer is like a built-in stopwatch in your microcontroller. Once you start it, it keeps counting up either in clock cycles, milliseconds, or microseconds, depending on how you configure it. You can set a timer to count up to a value and overflow. Trigger an event when a match value is reached. Generate waveforms using PWM. Timers are non-blocking, which means your main code can keep running, and the timer will work in the background. There are different types of timers, 8-bit, 16-bit, or 32-bit, depending on the counter size. For example, Arduino Uno has timer 0, timer 1, and timer 2. Timers operate in different modes. Normal mode, the timer counts up and resets on overflow. CTC mode, clear timer on compare stops and resets when a specific value is reached. PWM mode, used for generating pulse width modulation signals, for dimming LEDs or controlling motors. Let's say you want to trigger an action every 1 second using a timer. You can configure a 16-bit timer in CTC mode, set it to match after 1 second, and let it handle the timing, no blocking, no delays. Now let's talk about interrupts, one of the most powerful tools in embedded programming. Interrupts allow your microcontroller to respond instantly to events, instead of constantly checking for them. Here's a real-world analogy. You're watching a movie. Suddenly, your phone rings. You pause the movie, answer the call, finish, and return to your movie. That's exactly how interrupts work. The processor is doing something, and an external or internal event interrupts it. It temporarily jumps to an interrupt service routine, or ISR, handles the event, and comes back to where it left off. There are different types of interrupts. External interrupts, triggered by pins, like a button press or sensor input. Timer interrupts, triggered when a timer overflows or matches a value. Pin change interrupts, detect changes on any input pin. Software interrupts, generated from code, intentionally. Using interrupts lets you build event-driven systems, perfect for low-power, real-time embedded designs. For example, pressing a button on pin 2 can be configured as an external interrupt. Instead of checking the button status inside the loop, the microcontroller will only react when the button is pressed, saving CPU time. Here's where things get exciting, combining timers and interrupts together. This is the preferred method to create precise periodic tasks without blocking the CPU. Let's say you want to toggle an LED every 1 second, but without using delay. You set up a timer in CTC mode, match it for 1 second intervals, and attach an interrupt to that match event. Every time the timer reaches the match value, the interrupt fires, and the LED toggles. Meanwhile, the main program continues running, handling other logic, reading inputs, or controlling communication. This combination is extremely common in embedded real-time applications, like motor control loops, data acquisition, and even operating system scheduling. Let's bring it all together with a quick side-by-side comparison of delays, timers, and interrupts. These three tools might seem similar at first, but they serve very different purposes in embedded systems. Let's break it down. First, blocking behavior. Delays are blocking, meaning the processor is frozen, it can't do anything else until the delay ends. Timers are non-blocking, they run in the background and let your main code continue. Interrupts are also non-blocking, they only activate when an event occurs and return quickly to the main program. Next up, multitasking. With delay, multitasking is nearly impossible. Timers allow multitasking because they trigger actions while other code continues. Interrupts are even better, they allow your system to respond immediately to external or internal events while multitasking efficiently. Accuracy matters too. Delays can be off by a few milliseconds or worse, depending on how busy your CPU is. Timers, being hardware-based, offer precise timing, down to microseconds if needed. Interrupts are also highly accurate, they execute almost instantly after the triggering event. Use cases? Use delay for simple tasks like blinking an LED. Use timers for recurring jobs like sensor reading, PWM generation, or precise time-based tasks. Use interrupts for event-based triggers, like handling button presses, receiving communication data, or reacting to sensor thresholds. And finally, complexity. Delays are super easy, one line of code and you're done. Timers take a bit more effort, you'll configure registers or use libraries. Interrupts are the most powerful, but they require careful setup and clean code to avoid bugs or system crashes. So here's the big takeaway. Use delays when you're learning. Use timers for efficiency. Use interrupts when you need speed, responsiveness, and precision. Understanding how and when to use each of these gives you a strong foundation for designing smart, real-time, and reliable embedded systems. Now that you understand how delays, timers, and interrupts work, here are some project ideas to put your skills into action. Motion detector with interrupts, turn on a light when motion is detected. Timer-based data logger, record temperature readings every 5 seconds. PWM fan controller, control speed based on temperature. Debounced button using interrupts, accurately detect key presses. By using these tools, you can build systems that are smarter, more energy efficient, and highly responsive. That wraps up today's lesson on interrupts, timers, and delays. Make sure to like the video, subscribe to the channel, and leave a comment if you found this useful or have any questions. Join us next time on NextEd, Nexaspaces Tech Education, as we explore more real-world embedded system topics. Until then, keep learning, keep building,